Hi guys, my name's Jamin, and this is going to be a little video on exponential growth and decay questions in mathematics exams. So, this is a really good question type to study a lot of because A, it's appeared in every HSC exam now. I've got for the last 5 years written on the slides, but really it's just always there, right? It always appears. So, it's guaranteed to be in there, and it's almost always exactly the same. Very rarely will they stray from a very basic question type, which I'll show you in a second. So it's very predictable, and it's almost assured that it'll be in there. So what this means is that if you know how to do these questions, it's easy marks for you, right? This is a great question type to know and know well, because it's very, very likely to result in a return on investment for you. It's very likely to result in getting marks, not like studying something that is almost guaranteed not to appear, right? So let's look at how we approach this topic, and let's start with a little bit of revision. So what this topic concerns is quantities that increase or decrease at a rate proportional to the amount of the quantity we already have. So, for example, population growth. The more people that exist, or the more people that there are, the more people there are having babies, and so the faster a population will grow. Populations don't grow in straight lines. It's not like we look at a population graph and it does this. No, populations do this. They grow faster and faster as time goes on. And this is exponential growth. And you can have a similar thing for decay. A lot of quantities don't decrease at a linear rate. They decrease more the more there is. And an example of that would be the breakdown of a radioactive substance, right? So this is exponential growth and decay, and we model it with an equation that takes this form here, where the derivative of a quantity, which in this case is just x, with respect to time, is equal to or proportional to the amount of the constant that's present, so equal to kx. The solution, so this is a differential equation, the solution to which is x equals ae to the kt. Now you can prove that this works really easily. If you go x equals ae to the kt, and then differentiate this, you get dx to t equals, now this k value is all that comes out the front, so you get k times ae to the kt. Now, of course, we've seen the back half of this before. This is just x, isn't it? So that's great. So all we do is we now write x equals kx. So that's the proof of the result. Now, that proof, that is taking x equals ae to the kt and differentiating to prove that this differential form works, can actually pop up in the HSC. So make sure you know how to do that as well. But that's essentially all the actual content. The only thing you need to know is that if we have exponential growth, that this constant will be greater than 0, and if it's decay, it'll be less than 0. And that's really the only difference between the two. There's no other new theory, it's just the idea of what these equations are modeling. So with that in mind, let's look at some questions. Okay, so we're going to start with a really typical question from last year's HSC. So we're given the info that a radioactive isotope of curium has a half-life of 163 days. Initially, there are 10 milligrams of curium in a container, and we're given that the mass in milligrams is given by an exponential decay formula where A and K are unknown constants. And the question set up here is that typical question setup I was talking to you about. It's almost always find the value of K, find the value of A, and then sometimes do something else with it. The first thing we should do in this question is notice the key parts. We start with 10 milligrams. We of course are given the equation. And we know that it has a half-life of 163 days. That'll come into it later as well. So our first job is to simply state the value of A. Now notice that it does say state, which just means you can say it. And this is obvious because it's also only worth a mark. When you see this, you don't expect any working, you don't want to do any working, you should just be able to state the value. Now A, in an equation that takes the form of x equals a e to the minus kt, an exponential decay equation, A is always just the initial quantity, just how much is there to begin with. So we can immediately state that A is equal to 10, and no other work is necessary. We're given the initial quantity, that is what we have. Now, the next part of the question is that given that after 163 days, only 5 milligrams of curium remain, find the value of K. And so this makes sense. The 163 days was the half-life, which means that in 163 days, the amount in the container cuts by half. We started with 10, now we're at 5, so this makes sense. All we're going to do is substitute those two values, the value of T being 163 and the value of M being 5, to find the value of K. So here's our equation. M equals AE to the minus KT. And we'll substitute M equals 5, A is 10 from the first part of the question, and then we have E to the minus 163K. That's the value of T substituted in. Notice we now only have one unknown. K is the only unknown, so we should be able to solve this and find K. It's not too hard. If we divide both sides by 10, you'll get 0.5. That's always your first step in something like this, to isolate the exponential. From there, we need to get this K out of that exponential. Now, you can consider this a few ways, but the way I consider it is that if we want to get rid of an exponential, we apply a logarithm. Don't have room there, so I'll just write with an arrow. If we take the log of both sides like this, on the left-hand side, the log and the exponential will cancel. Just like a multiply and divide would cancel, or a square and a square root would cancel. A log and an exponential will also cancel. And on the right, we just have the natural logarithm of 0.5. From here, we're pretty much done. We just have to divide by that negative 163. Now when we do this, we get a value in the calculator of 0.004252, etc. Now they haven't specified how many decimal places they would like. Let's give them at least a couple of significant figures. I'm going to go to 0.0043. And that is our final answer. This is a really easy 3-mark question, guys. This is not targeting Band 6 students. It's very accessible. Stating the value of A, if you remember that A is your initial quantity, that's a guaranteed mark. The rest is just substitution and a little bit of algebra. As long as you remember to take the logarithm in this step in the middle here, then that's really the only tough part about it. The rest is fairly easy. This should be a 3 marks that everyone who watches this video should be able to access. So that was an example of a question that would appear towards the middle of your paper, a standard one. This one is something that could appear later if they wanted to challenge you just a little bit more. This is from a HSC paper in 2013. In this case, we're actually given 2 forms of exponential growth and decay. We're given 2 equations to deal with at once. So the scenario is that we're given a lake and it contains a set number of trout at the start when we start. Then at a certain time, we introduce 10 carp, and what that does is the carp starts to exponentially grow. Their population is subject to exponential growth, whereas the trout starts to exponentially decay. Now, the exponential decay formula we're given looks a little different than normal, but that's okay. It'll obey most of the same principles. And the carp is given to us in a more standard formula that looks a bit like this. Now, the first few questions are fairly stock standard, and then we get to some harder stuff at the end. So take a second to look over this question, and let's get into it. Okay, so the first few questions concerns the population of trout, the equation for which I've got in the top left there. So the first question is, how many trout were in the lake when the carp were introduced? This is a fairly easy question, because all it is it's a substitution of t equal to 0. So if we go t equals 0 here, we get n equals 375. Now remember, don't immediately jump to 375. A lot of students did. When we look at this, if we sub t equals 0 into our exponential term, we pop t equals 0 here, that turns the whole exponential into 1. E to the power of 0 is 1. So the answer is 375 minus 1, which equals 374. The next part of the question is asking when the population of trout will be 0. This is now the other way around. We're substituting n equals 0 this time. So we go n equals 0, and this is very similar to the question that we got last time in terms of how we're going to solve it. It's very similar. We're going to have to apply a logarithm. So the way we do it is we go 375 minus e to the 0.04t is equal to 0. So we get e to the 0.04t is equal to 375. Just like before, we take a logarithm, and that gives us 0.04t is equal to the log natural of 375. Then dividing by 0.04 and getting a calculator, we get 148.17 days, and that's to 2 decimal places. So 2 fairly stock standard questions, and you only get 2 marks for those 2 questions together. The next one is a little bit more interesting. Sketch the number of trout as a function of time. So, just put our set of axes here. So you would expect, and you should, put time on the horizontal axis and put n on the vertical. And we know 2 bits of information already. We know that n equals 374 when t equals 0. So that gives us a vertical intercept. We also know that it takes just over 148 days for the trout population to reach 0. So that gives us a horizontal intercept. It's the shape between there that is going to be the issue. Now, a lot of students would do this. Yeah, that is what a lot of students would do, because that sort of suits the exponential decay that we're used to. This is not that. Notice that the equation that we're given up here, this is not a typical exponential decay formula. This graph doesn't look like that. So we'll put a cross through that. What this graph looks like is a little bit more like a parabola. It actually looks like this. The reason we know that is because what we're doing here is we're subtracting an increasingly large exponential from a constant number. So at t equals 0, that exponential term is just 1, right? So we're subtracting 1. Then as t goes up, this term gets bigger, that exponential term. So we're subtracting an increasingly large amount. And that amount is that's actually exponential growth, right? What we're subtracting is exponential growth. So this is a weird form of exponential decay where we're not directly decaying the quantity, we're subtracting an exponentially growing quantity. And you could even substitute a few values in if you wanted to. The logic tells us that that is the shape of the graph. Right, now this next question is tougher, and it's worth 3 marks, so you'd expect that. When is the rate of increase of carp equal to the rate of decrease of trout? Now, to set this up, we're going to need to do a little bit of investigating on the dp dt formula we were given in the question. So we were given that dp dt, the rate of change of the carp's population, is given by 0.02p. We want to get it back to a regular form equation, just a p equals blank. And we can do that fairly easily because we know that this equation has to be in the form kp, right? That's what exponential growth equations look like. So that is immediately the value of k, 0.02. The other thing we know is that we initially had 10 carp in the lake. When we introduced them, we introduced 10 of them. So that then gives us that a equals 10. So immediately from that, we can form the equation that p is equal to ae to the kt, the exponential growth, and that therefore p is equal to 10e to the 0.02t. So that's the sort of setup. We now have an equation for n and an equation for p. The other thing we'll need is an equation for dn dt, the derivative of n. And we differentiate this as normal. We would get negative 0.04 e to the 0.04 t. That first constant there, that vanishes, right? Okay, so what we're after here is when the rate of increase of carp is equal to the rate of decrease of trout. Now, let's think about this carefully, because the default response would be, okay, dn dt, the rate of decrease of trout, is equal to the rate of increase of carp, to p to t. But if we think about this carefully, this can actually never be true, right? Because the rate of decrease of trout is a negative quantity, and the rate of increase of carp is a positive quantity. Of course, one's a decrease, one's an increase. They can never be straight equal to each other. Positive numbers don't equal negative numbers. What this question's saying is that the magnitude is the same, that trout is going down as fast as carp is going up. So what we actually have to do is take the absolute value of both of these quantities. That's the bit that's hard to get, taking the absolute value. But it's because we don't care about sign. We care about size, right? This doesn't really do anything complicated. All it does is it takes the negative off of our dn to dt. So it's just 0.04 e to the 0.04t without the negative. And as for the right-hand side, well, we know that the derivative of p with respect to t is 0.02 lots of p, which we now have an expression for. So we'll tidy up that right-hand side, and what we get is 0.04 e to the 0.04t is equal to 0.2 e to the 0.02t. And our job here is to solve this equation. So the first thing I'm going to do is divide both sides by 0.04. Now when you do that, you can use a calculator, and you get e to the 0.04t on the left, that's now isolated, and on the right, 0.2 divided by 0.04 is quite a nice number actually. It's just 5e to the 0.02t. Now the next step is I'm going to divide by e to the 0.02t. Now I'm allowed to do this because an exponential term is never equal to 0, so I'm allowed to divide by that. What that gives me is e to the 0.02t. Keep in mind that when we divide exponentials, their indices subtract. That's the index law of division. So we get e to the 0.02t is just equal to 5. Then from there, we do what we've done a few times in this video already. We take a logarithm, and then we use a calculator to find the answer, which in this case, to 2 decimal places, is 80.47 days. So it's after 80.47 days that the rate of increase of carp is equal to the rate of decrease of trout. This is probably the hardest question that's ever been asked on exponential growth and decay. So if you understand this and you think you could do this in an exam, then you're sitting really nicely on this topic. Now this last question is a little bit more algebraically intensive, but a lot conceptually easier to understand, right? So it's just, when is the number of carp equal to the number of trout? So all you do is you put our earlier expression for carp equal to the expression for trout. It's really that easy. Now, actually solving this is a different thing altogether, because what this is an equation reducible to a quadratic. To make that more obvious, let's move everything to the left-hand side. So we just slide the two exponential terms together and put the constant next to them as well. And this sort of looks like a quadratic. To make it more obvious, let's let m be e to the 0.02t. Now when we do that, we get this first term, that's m squared, because remember the index law of a power to a power is that they multiply. So e to the 0.02t squared is e to the 0.04t. So that first term is m squared, the next term is 10m, and we're subtracting 375. And from here we turn to any method you normally use to solve a quadratic. This particular one factorizes to m plus 25, m minus 15. You might spend 30 seconds figuring that out or jump to the formula. It's really your choice. So we get m equals negative 25 or m equals 15. And at this point, we substitute our exponential back in. Now, it doesn't really make sense for there to be two answers, and indeed one of these doesn't work, and it's the one on the left. Exponentials can't be negative. If you think of the graph of an exponential, it's always above the axis. So an exponential can never be negative, so this bit has no solutions. It's the right-hand equation we care about, and again, we're taking a logarithm and then dividing. This process of using a logarithm to cancel an exponential and then rearranging is really common. You need to know how to do this. And we pop that into the calculator and we get 135.4 days. Notice I'm putting units. That's really important to make sure that they know, the marker, that you know what you're doing, that you're responding to the question properly. So it's after that many days that the number of carp is equal to the number of trout. So that's the answer to this question. Again, this is probably the hardest question collectively that they've ever asked on exponential growth and decay. It's a really easy topic most of the time, at least in comparison to other stuff that can be asked. But every topic, they can always throw curveballs like this one. So make sure you're ready for them. In terms of a few last minute tips for these sort of questions, do keep in mind they are some of the easiest marks in the HSC if you're prepared, because they are so predictable. It's always state a value of A, find the value of K, and then perhaps do something else with it at the end. And that something else at the end is almost always easier than what I've shown you. It's really, really important to be prepared for this question type because it's guaranteed to be worthwhile for you. Be sure to answer the question at hand, especially in the question we just did. Very easy to get lost. Always keep in mind what you're being asked, and don't forget units if you need them. Besides that, this is very much a practice makes perfect topic. So if you have any questions on stuff you find in past papers or in anything in the material you're studying for your exam, be sure to come and let me know and I'll help you out. You can find me on the ATAR Notes Mathematics forums and I'll be there to answer any questions you have.